All right, in this video, I'll be going through the learning objectives associated with Kirchhoff's law. Four learning outcomes associated with this chapter. First is to recall and apply Kirchhoff's laws, to use Kirchhoff's laws to derive the formula for the combined resistance of two or more resistors in series and in parallel. Recognize that ammeters are connected in series within a circuit and therefore should have low resistance, and recognize that voltmeters are connected in parallel across a component or components and therefore should have high resistance. Here are Kirchhoff's laws, statements of them, agreeing with sort of the language that was on the chalkboard on Friday. So Kirchhoff's, and it is important that you remember them in this order rather, because you could get a question that says, state Kirchhoff's first law. And so while the physics doesn't care sort of which order they're in, so like the universe doesn't matter what order we sort of remember these laws in, you as a student of physics may be expected to sort of state Kirchhoff's second law. So you have to know that that second bullet point up there is the one that we call it second law. The first law is a consequence of the fact that charge is conserved, like mass energy, like momentum. It's one of those quantities that's conserved in the universe. We don't destroy charge. And so because charge is conserved, the sum of the currents entering any point in the circuit is equal to the sum of the currents leaving that same point. Mathematically, we can say the sum of the currents in equals the sum of the currents out. And they say at any point in a circuit, sometimes they'll call that point a node or a junction. Okay, it's like a point in a circuit where there's multiple connections. Kirchhoff's second law, you may recall, hopefully it's written down in your journal already. The sum of the EMFs around any loop in a circuit is equal to the sum of the PDs around the loop. And we can shorthand that by saying the sum of E equals the sum of V, where E is EMF and V is the PD, the voltage. They're both voltages, remember, but it's like the energy consideration is here's where we put energy into the circuit. We converted other forms into electrical energy, the EMF, and the PD is where we took that electrical energy and converted it into other forms in the appliance, in the device, in the component, in the resistor. So both are voltages, both energy per charge, and the sum of the energy per charge into the circuit, the EMF, equals the sum of the energy per charge out of the circuit, the PD. Kirchhoff's two laws. You need to know them, and then we'll apply them certainly all over the place. But just being able to state them, that's worth some marks too in certain things. These are some other lesser known Kirchhoff's laws. Kirchhoff also had a law against smoking and swearing. And of course, the sum of the volts around any loop is zero and the sum of the current that they're in node is zero. But also no skateboards, no headsets, no gum, talking food, or drinks. And the students are like, was he got like some chains back there, pistol on his hip? Don't mess with Kirchhoff, okay? You meant business. I really don't know. I think that they've maybe, that's sort of the point of the caricature, right? They've exaggerated some of the Kirchhoff's laws there. So Gustav Kirchhoff. Here's some like old tiny type writing with the same physics that we've already kind of got down. The current in all parts of a series circuit has the same magnitude. Like the total current is, it's like I1 minus I2 equals I3 equals etc. Okay. You can't have, remember, we can subtract the current away if it goes in the opposite direction. Current is a vector. And so when we derived it, for example, the equation for parallel circuits down here, right, we considered sort of the current going in sort of one direction, the current going in the other direction, and there was no EMF. So anyway, these are some slides that I just sort of stole off of the internet, typing in derive, Kirchhoff, derive formula for combined resistance. And, you can kind of read through this here, but I would sort of use the chalkboard derivation that we had on Friday. Again, you should sort of recognize these symbols here. The electrons sort of going through. There's half an amp of current in this circuit. This is the source of EMF. a 3-volt drop across this one, a 4-volt drop across this one, and a 5-volt drop across this one. So we have 12 volts of EMF, right? They show that there, 12 volts of EMF. And you can see that the voltage drops sort of equal that. Here they've sort of applied this sort of rule here. You can add up the total resistance, calculate the current. That's the same everywhere, half of an amp from a 12-volt EMF and 24 ohms of combined resistance. And then the voltage drops, right, which is the V equals IR. So the voltage drops across each resistor. Those are the PDs right here, 3 plus 4 plus 5. Those are the PDs. They add up to the EMF 12 volts, right? So that's sort of seeing Kirchhoff's second law. The fact that the current is the same everywhere, right? We factor out this sort of common current is a consequence of Kirchhoff's first law, right? The current going into this sort of ammeter come out of it. The current goes into this R1, comes out of R1, and so on. So around those. The potential difference across all branches of a parallel circuit has the same magnitude. We kind of saw that. And again, we can factor out the common term V, right? So if it's I equals V over R, then V is sort of the common factor. We can factor out and get the sum of the reciprocals for reciprocal circuit resistance. The R sub EQ, the equivalent resistance in the circuit. So just sort of remember this equation here. It's good to sort of know each of them for series and parallel. And I will actually post another video where I kind of go through that derivation a little bit more cleanly than I'm prepared to do right now. So click the link right there if you wanted to take a closer look. And I really got to remember to make the video. So click what link? Hopefully there's a link there. Recognize that ammeters are connected in series within a circuit and therefore should have low resistance. If you don't already have some kind of a schematic like this in your notes, sort of agreeing with what I drew on the chalkboard, I drew sort of like a parallel circuit with 2 resistors, R1 and R2, and I put voltmeters across each one of the resistors and ammeters in each branch and an ammeter sort of outside of the battery with a voltmeter across the battery. It's like if we just have unlimited ammeters and voltmeters, you know, we can measure this sort of the current everywhere. But this is a correct wired circuit diagram. Sometimes you'll get a multiple choice question. They'll say, you know, which one of these circuits is wired correctly? And you're looking for the key thing, the ammeter in series, right? The ammeter has to be a part of the circuit. And you're always looking for a voltmeter like this across a component, like it's across this lamp here. To say, okay, the PD across this lamp should equal the EMF across this battery, right? Like if I plug this voltmeter in over here, whatever number I got, let's say it's 3 volts, should equal the 3 volts dropping across this, right? And the ammeter would be whatever the current is sort of through that based on the resistance of this. Ohm's law. So you want to have a figure like that where you're making a note to yourself, voltmeter always like this in parallel, right? So there's a parallel sort of line with whatever we're measuring across that thing. Ammeter in series, current through. Ammeters measure amps of current through, and then just whatever kind of language, and it's very redundant. I realize that, like saying the same thing over and over again. That's because it helps to reinforce sort of the correct physics there. So you do kind of want to talk your way through it, you know, and then not just have this circuit standing by itself in your notes. Or just like, okay, you know, what is this for? What's the point of drawing it? To show the placement of the ammeter and the voltmeter, and maybe an explicit note to your future self. Hey, when you see circuits, look for this, you know, for correctitude, correctness, veracity. Look for it for veracity, truthfulness, correctitude. Correctitudinal of this. Recognize that voltmeters are connected in parallel, so that's sort of, you know, this one was the language on the ammeter, but there's also a voltmeter there. Here's the kind of what they really look like, right? So you have some voltage source here. I've never seen a battery looking like that before, but okay, maybe a battery. And then they've got the ammeter, and see how it's just like a part of the circuit, right? Like they've just connected it like one more component into. It's really the resistors, right? That they've got. The point of the circuit is to resist the flow of charge. You got some resistors here. And it looks like they've wired this voltmeter where? Is this voltmeter measuring the voltage across this one or this one? Excuse me. This guy over here, right? Like if you look at how it's wired, and there's a lead on this side of this component, and there's the other lead on this side of this component. So it's measuring it across this component here. Okay, so it's like we want to know the voltage, say, across, like what's the voltage drop across this one? And it's part of the total voltage here, right? The rest of the voltage would drop across here. Almost no voltage would drop across this ammeter. Why? Think about the essential question, because it has really low resistance. And so V equals IR, that's the voltage drop, right? V equals IR, Ohm's law. This thing has very, very low resistance. Its R is very, very low, close to 0. Okay, so it's designed to have low resistance so that it's not going to have too much of a voltage drop across it. Okay, just lets the current flow through, almost 0 resistance, and so almost 0 volts drop. The voltage drop across it, in fact, is negligible if it's a well-designed ammeter, right? We don't want there to be volts dropped across this because we want to actually measure the voltage drops across the resistors. So we just let the current flow through. The ammeter doesn't resist the flow of charge. Its resistance is close to 0. No voltage drop across it. Likewise, hardly any current flows through the voltmeter. Now, some current sort of has to flow through it to power it, but it has really, really high resistance. So hardly any current flows through it. Okay, it's designed to really measure sort of the voltage drop across the resistor here. So as the current sort of gets to this node, that's like a parallel circuit, right? It's like, oh, some charge goes through this way. Some charge is always going to go, even if this thing has a resistance of 1,000,000 ohms. Some small fraction of charge will go through that 1,000,000 ohm resistor. So the voltmeter has really, really high resistance, so it hardly draws any current through it. Okay, so basically the voltage drop across it is the voltage drop across this thing that you're trying to measure. Right, that's sort of the point of the voltmeter. We want to know what is the voltage across this thing. So hardly any current goes through it because it has such high resistance. And then you can also see this component. This is called a switch. And when it's closed, then the current can flow through. And if it's open, it just can't. Right? It's like air, right? The current's not going to flow through the air right here because air is a pretty good insulator. So this is just a convenient way to sort of power off and on the circuit. We don't have to like disconnect a wire out of our voltage supply, or the other way to do it. So we can sort of think about this schematically. Practice. If we saw a circuit like this and it said using the conventional circuit symbols, we can sketch a circuit diagram of the following illustration. Let's go ahead and do that. So you are expected to know sort of the basic circuit symbols. If you ever come across one, it's like, oh, we haven't seen this one yet. What does this one stand for? What's this one mean? Be sure to ask those questions. All right, and so I always like to start at the voltage source. Like something's got to be powering this circuit, right? And so I'm just going to kind of sketch this circuit off to the right over here. So a voltage source, this is negative, this is positive. So a longer line for the positive, right? Sort of like a plug in the wall. That's the symbol for a voltage source. The other symbols we've seen are this one, like two open circles like this, and you sort of label them, and the circuit sort of gets connected like that. Or you can just use lines like this. Sometimes it is a battery of cells, okay, so it'll kind of look like this, and that's just saying there's a lot of batteries here, okay, but this is still negative, this is still positive. You can wire up batteries so that they cancel each other out, right? Like you do positive to negative, negative to positive, and you have a 1.5 volt battery, and you have negative 1.5 volts, and you basically cancel out the voltage. So I don't know why you want to do that, but it is possible. All right, so we have some voltage source here, and then I'm going to go sort of anti-clockwise around the circuit here. I'm going to go anti-clockwise. A switch has this symbol, okay, where it's like a switch that you break open, so it's just like a line that's disconnected, and it's understood that, oh, I could connect it if I wanted to. So this symbol right here for the switch. And then it goes around to the resistor. Remember, there's two symbols that we said we could kind of use for resistor. Sometimes it's convenient to just draw little boxes because then we can like put the values inside of them, like how many ohms of resistance. So it's also like R1. And then it goes around to another guy over here, R2. And then it goes around to an ammeter, connected back to positive. And don't forget to put your voltmeter in parallel with this resistor right here, right? So this would be sort of the circuit diagram. Remember the other symbol for resistor is this guy right here. Okay, that means the resistor. So like we got a straight wire where we want the charge to flow through. Then we get to a resistor where we're resisting the flow of charge and the charges get slowed down and all this sort of. Remember, they're just pieces of metal. The metal here, like I equals nave, the current goes through. We got a piece of metal with number density, N, and it has current I equal to that number density times the cross-sectional area times the mean drift velocity times the charge. The resisting wire has an equation sort of governing it. Resistivity equals resistance times area divided by length. And so the resistance of a piece of metal like this is really equal to that. So if we make them longer or we make them sort of wider, and of different metals, right? Resistivity is sort of like a property of the metal, depending on what type of metal it is, it has a certain resistivity. But then we take that metal and we make it a certain length, right? So we sort of, wind it up and wrap it around, sort of inside a little piece of plastic, right? And that's what a resistor is. And it just has different areas, different cross-sectional area, different lengths, and it gives it sort of different values of resistance. All right. I think that's the end of the slides. Here is a question from paper 2. Distinguish between e.m.f. and potential difference. And so that's 6A, and you probably go on to do sort of more with it there. So just imagine, that how well that question aligns with the learning objective, where it's like students will, recall the difference between e.m.f. and PD, or students will distinguish between e.m.f. and PD using energy considerations. Right? I think it's the exact language of